Okay, can you all hear me now?
Yes.
Okay, sorry about that. Um, so my name is Gagnebin, and I'm at California State University, Sacramento. And today I'm going to be talking about the work that I've been doing on modeling exoplanet atmospheres for JWST spectroscopy with Picasso. And so this work was done with Shaknik Mukherjee and Dr. Jonathan Fortney at the University of California, Santa Cruz, and then the code based off code written by Natasha Batala from NASA Ames Research Center. So in the first cycle of pointings for the James Webb Space Telescope, there are over 70 exoplanets that are set to be observed by the ERS, the GEO, and the GTO programs. And so a number of these are sub-Neptune to Jupiter class-sized gas giant planets, which is what I'm focusing on in my work. And so the reason that we focus on gas giants is, one, that they're easier to detect using most common methods that we have. So like the transit method and also radial velocity. These hot gas giant planets specifically, they're large and they're close to their stars, so they block out more light, easier to see through transit. And they also have more of a gravitational effect on the star, which makes them easier to detect through radial velocity. And then this code also was initially designed for objects with hydrogen-dominated atmospheres, so those would be brown dwarfs and then these gas giant planets as well. So we've already started to see the benefit of using these larger gridded models, which is what I'm generating in my work. So already, even since just in the first year since its launch, James Webb has been used to with these self-consistent atmospheric model grids to detect molecules in the atmospheres of distant exoplanets. So there have been several up to this point. One of these is WST 39b, which is a hot gas giant, so it's close to its star, about 700 light years from Earth. We can see on the right here the spectrum that was released by the James Webb Space Telescope. So you have the data points in white, and then this best fit model in blue. So this was fit again to these grid of models, and we were able to detect sodium, water, carbon monoxide, carbon dioxide, sulfur dioxide, other elements like that. And so we've already really started to see the benefit of using these grids of models. These models tend to be physically consistent, so they would be what we would actually see in the atmosphere. They also put retrievals in physical context, because retrievals would just give you like the abundances and the presence of molecules, but these grids actually give you physical context as well. And they're also useful in modeling observations and preparing observing proposals. So we would to know whether or not this candidate is of interest, you'd be able to model it beforehand. And so this code is a open source Python one-dimensional, that it creates one-dimensional radiative convective thermochemical equilibrium models. And so what it really does is it starts with this isothermal atmosphere, and then it makes these changes using inputs from the star and from the planet, and it makes changes to the profiles and the physics of the atmosphere in order to get something that would be physically consistent with what we'd actually see in the atmosphere. And then there's a link to the GitHub here if you're interested. And so using this code, we are able to get several different things. So one of them is a temperature pressure profile. So we can see all of those on the right there. So in the top left, you see this temperature pressure profile, which really would just show you the temperature at each pressure level in the atmosphere. And these are all for a model planet that's Jupiter size, Jupiter class, and is close 0.1 AU away from a sun-like star. And we would also get the chemical abundance of the atmosphere, so it would be just like the abundance of different molecules in the atmosphere. And then 3 different types of spectra. So you would have reflection spectra, which you can see on the top right, which is measured based on the changing reflectiveness of the planet as a function of wavelength as light is reflected off of the planet. And then on the bottom left, you have the transition spectra, which is measured as a function of transit depth as a function of wavelength as the planet transits in front of the star. And then the thermal emission spectra on the bottom right, which would measured as a change in thermal flux as a function of wavelength as it passes behind the star, so in this secondary transit. And so we are looking at over 50 exoplanets that we want to model. So those are the gas giant planets that James Webb is going to be looking at. And so for each of these planets, I'm creating a grid of 150 different atmospheric models. So those are based on changing 4 different variables. So the first is metallicity, which is just ratio of metals in the atmosphere to hydrogen in the atmosphere. And that really just impacts the depth we're able to see into the atmosphere, and then also what spectra we can see as well. I'm also changing the carbon to oxygen ratio, which is the ratio of carbon to oxygen in the atmosphere, and it shows what elements or what molecules, again, we would see in the atmosphere. So a ratio greater than 1 would mean that there's more carbon, so there would be less water vapor, because oxygen would kind of be tied up in elements such as like carbon monoxide, carbon dioxide. There'd be a lot of methane, and a ratio less than 1 would mean that the atmosphere is water vapor dominated, or it's water dominated, so there'd be less like methane because there's less carbon available. And then I'm also changing the heat redistribution factor. So that's just a measurement of essentially how much energy is lost from the star on the planet to the night side of the planet. So we're considering that these planets are tidally locked. So a value of 1 would mean that we're modeling the day side, there's no energy lost to the night side. A value of 0 would mean that we're modeling the night side. And then 0.5 would be an average over the entire atmosphere. And then the final thing I changed was the internal temperature just of the planet itself. And I used 2 different values for that, 100 and 300 Kelvin. So I've already modeled 6 planets so far, and those are shown on the left. And for all of them after HD 189733b, I used this grid of 150 different models. For HD 189733b, that was the first one that I ran, so I was just kind of tweaking it a little bit more because this is a well-studied planet, just to make sure that everything was working well. And then I'm in the process of running HD 149026b, and that's one that we're going to be able to publish in a paper, and it will include both emission and transmission spectra, and then just all of these models as well, of these 150 different models. And then if for any of you who would like to are studying planets using James Webb, if you have any models that you'd like to be created, you can feel free to contact me. My email's right there, and I'll run those for you. But so one of the first planet that I modeled using this 150 different model grid was WASP 69b, which is a hot Jupiter around a K-type star. So I'm going to have some plots for those. So these really just show the effects of varying the different variables that I used. So on the left here, we have the temperature pressure profile with varying metallicities, and you can see that high up in the atmosphere, lower metallicities tend to have higher temperatures. And then it kind of switches as you get deeper in the atmosphere, close to the planet. Higher metallicities have higher temperatures at each pressure levels. And then for the transmission spectrum, you can see that, like for carbon dioxide, for the light at carbon dioxide, higher metallicities tend to have like kind of deeper spectral features, and then lower metallicities have deeper features for methane. And then for varying the C to O ratio, high up in the atmosphere and also deep in the atmosphere close to the planet, a lower C to O ratio tends to have higher temperatures at each pressure level, and that kind of switches in the middle, where these lower C to O ratios have lower temperatures at each pressure level than the higher ratios do. And then on the right in the transmission spectra, the higher C to O ratios tend to just have stronger spectral features overall across all wavelengths. And then for the heat redistribution factor, kind of a similar thing. A higher value tends to have higher temperatures at each pressure level because there's less energy lost on the night side. And then they also have just stronger or higher value spectral features overall in all wavelengths. And then finally, varying the internal temperature of the planet, you get for the temperature pressure profile, these higher temperatures of the planet tend to have higher temperatures at each pressure level, especially towards the deeper the atmosphere, closer to the planet, and it doesn't really impact the spectrum. And so, again, I just created a grid of 150 different models for each of these 50 plus gas giant planets, or I'm going to, that will be observed by James Webb in cycle 1. And then after these models are created, they will be published for use by the scientific community. So that will really just, they can be compared with data taken by James Webb, and they'll really just show us the makeup of the atmosphere. And they can also be post-processed with disequilibrium chemistry. So we're assuming thermochemical equilibrium, but you can kind of change that and make the atmosphere changing. They can also be post-processed with clouds. They can be used as inputs into photochemical models, which would give you more exotic molecules, and they can also be used in grid retrieval frameworks. So kind of just fit with. Yeah, that's it. Is there any
Perfect.
questions?
Thanks a lot, Anna. If there are any questions, I don't see questions about that talk yet in the Slack, but first, congratulations. It's a really nice talk and really nice work. My question was actually going to be about disequilibrium chemistry. So if someone has a question, you can raise your hand. Otherwise, maybe like a small question. When you say you will publish about these results, will you publish, like, will you make publicly available the spectra, or also everything about the underlying atmosphere, like the profiles of the abundances and the temperatures and things like that?
Yeah, it
I
would
imagine
be.
it's probably going to be all of it for the post-processing, but
Yeah, definitely. I'm pretty sure that we will be making everything available. Definitely the temperature pressure profiles and then these different spectra as well. And those will be published. Like we're gonna start working on a paper. I'm working on running the models for the HG149 planet, and then that'll be published as a paper.